Okay, we're going to start the sequence and attention mechanism. So this lecture covers machine translation, sequence model, and attention mechanism. First of all, the machine translation part. So this work is in part motivated by Rosetta Stone that was discovered a while ago. And this stone has 3 different languages, and they represent the same meaning or same content. The topmost part includes text from ancient Egyptian, particularly hieroglyphic scripts. And the middle part is also ancient Egyptian, but in different form, called demotic scripts. And the bottom part is consist with ancient Greek language. But since they have the same meaning, the researchers were able to map basically the content of different languages and try to figure out how to translate from one language to another language, from example, from Egyptian to ancient Greek. This shows some history of machine translation. Very long time ago, there was a movie about machine translation. It was 1954. How to translate Russian to English. They call electronic brain. And if you look at this timeline, in 1954 to 82, the popular approach was basically rule-based, handmade rules that translate one phrase to another phrase in different languages. And for a while, there was statistical techniques from early 1990 to early 2000. There was a statistical MT, phrase-based approaches, and so on. There, if you go to conferences, machine learning or natural language processing conferences, most of them discussed about statistical approach. And since after 2016 or 2017, after the deep learning technology was more developed based on the backpropagation algorithm that can effectively train the network, this also instigated the research in machine translation, and the neural approaches kind of dominates now various applications from machine translation. Now let's look at briefly about statistical machine translation. It's basically learning statistical models from data. For instance, given French language sentences, let's say X means French, and let's say Y is English sentence corresponding to that sentence. And what we're trying to find is, given X, particular French sentence, what is the Y that maximize this probability? There is the argmax. Whatever this is, it should maximize, whatever the Y is, it should maximize the probability of this mapping. And using the Bayes theorem, this can be separated into these 2 different probabilities. Remember this Bayes theorem? So this can turn into this probability X. Instead of probability Y given X, it can turn into X given Y, and probability of Y, and divide by this probability of X. But oftentimes we ignore the denominator, the bottom part, because it's a probability. Once we know the probability up top, we can just adjust based on the ratio to make it as a probability. And anyway, here we're trying to find why they maximize these two parts together. And the first part is translation model. How a particular phrase or the word is mapped to a different phrase and or words in a different language. So it needs the parallel corpus to train this model. The other part is the fluency, the language model. How natural the language is, how fluent the sentence is. So this can be trained basically in this case English. If you have a lot of English sentences, we can measure how fluent, how consistent this why particular sentence is. So the left-hand side, French to English, then the right-hand side, the language model. If you just map French to English, like a phrase, part of phrases and part of word separately, and this will be some set of English phrases and English words. It could be broken English. So here is a sentence from French, and this will be kind of a list of words that map to particular, maybe Hamburg will map to hunger or something. Where could mean what and so on, but still maybe not like natural English sentence. And given this, we make the most like a natural sentence out from this pool. Now, the left side is called translation model, and right hand side is called language model. And decoding algorithm basically that creates the translation output is, as I mentioned earlier, this argmax equation. The translation model starts with segmenting input into multiple words. So here, basically, again, it's based on the parallel corpus, and how the target is how it translates each phrase into the phrases in the target language. And in this case, le programme arrête mise en application, and you can see the mappings basically. Bin has mapped to ete, and program is mapped to program, and is mapped to lo, and so on. And this may not fully attention to the particular fluency yet. It's just mapping a segmentation of the given sentence into word or word phrases, and then mapping. And if we represent the alignment into some vectors, here is one way. So if you make this has like we create a numbers out from each word, like 1, 2, 3, 4, 5, 6, then this particular le could map to number 2, and program map to number 3, and these 3 word parts could be mapped to this particular 666. And this vector, the length of vector will be basically the length of the sentence, the size, how many words. And in the old statistical machine translation, this alignment was very important. So they create this kind of alignment structure that corresponds how the words are mapped to each other, like we saw in the earlier slide. The Japan is mapped to Le Japon, but Le is not, this particular pronoun is not used in English. So it can be a spurious word. It's not mapped to anywhere in English. But in this case, it will be mostly one-to-one mapping, but in some cases, it could be one-to-n mapping or n-to-one mapping, like in this case, or it could be n-to-m, like arbitrary clusters of words could be mapped to arbitrary cluster of words in other language. Here's a many-to-one, for instance. So there are 3 different English words mapped to one French word, one-to-many mappings. So as you saw in the example, it's implemented, could be mapped to mission application, so one-to-many, and this could be sometimes called a fertile word, and even many-to-many. So it cannot be broken down into one-to-one mapping. It has to just altogether map to a cluster of words. This altogether map to these 2 words in French. And imagine how you maintain all these mappings. It could be very time consuming, and at the time we need a lot of linguists doing this kind of work. And if you have many languages and we have to create mappings across all these languages, this work could be very, tremendous. And now we go to the language model part. We are trying to find the good representation, natural representation of the same meaning. So we say good sentences. And language model oftentimes means unigram, bigram, trigram, fourgram, and so on. And if we look at this, it could be represented as probability of trigrams. So if there's one word, it's just probability of Mary. If there's 2 words, then it will be a probability of seeing did given Mary. And then we have trigram, probably not given Mary and did, and so on. We'll calculate all this probability and try to find the word orders that maximize this probability. Right? The probability trigram. And this probability is computed based on the English corpus, like with many English sentences. And by combining these 2 together, the translation part and then language model part, and we need to find why they maximize these 2 probability together. And how do you compute this and all possible combinations? There are so many ways this could be happening, and also different possible word mappings and possible word orderings. And it's very expensive. If you think about the search space, this combinatorial could be combinatorial search. So sometimes you use a heuristic search to find something more reasonable and discard all the path that has low probability, and but still maybe very big job. And the statistical machine translation used to be a very big research. There was a huge research effort, and in academia. And you can imagine that those maintaining all these tables and tricks. It was extremely complex system, and there are many different techniques combined. And there are separate modules, for instance, like English to French, English to German, English to different languages, and all these components together. And it needs a lot of feature engineering because particular language has particular features. You have to maintain all these feature maintenance modules. And in order to maintain, so language change over time, you have to maintain, and new words may come. And you have to maintain all these tables, tables of equivalent words. And since we have many possible language pairs, it has to be repeated for all these language pairs, like English to French, English to German, Korean to Japan, Korean to Chinese, Korean to English. All this efforts has to be repeated. And just one representative metrics for MT is BLUE, Bilingual Evaluation Under Study. And this is often used for measuring the translation quality. And what it does is basically it looks at the output from MT and compares that with the human experts translation, and see how similar to human translation. And how we compare that? We use dissimilarity using n-grams. Let's say if we have the output, and then this is a machine and humans output, and we compare by using bigrams and trigrams. And as you can imagine, this may be not effect, but it still is used because there's not many alternatives. Much better. There are alternatives, but not much better alternatives. And in this particular one, gives penalty if this translation is just too short. That bigram and n-gram may have a low scores, so it may create overall low BLUE scores. So BLUE score is useful, but it's not perfect because human can have multiple different ways to translate the languages, right? Even for English to French, French to English, Korean to Japanese, there are multiple ways. And if it's just strictly using n-gram, there might be not many overlaps, even if they are good sentences. So even if the results may be reasonable, it may get low BLUE score if it happens to be not very similar to the given human's translation. So now we'll move on from statistical to neural. The neural machine translation different because it's just using a single neural network instead of multiple components. And remember, in statistical machine translation, it has at least two components. In each component consists with multiple different tables, different modules, and so on. And this new one, well, compared to the old one, is called the sequence-to-sequence model, or it's called encoder-decoder model. So there's input sentence, and we'll create output sentence in one system, one-to-one. And there will be middle, the bottleneck. This gets, the information is all kind of going to this particular point, and then given this will generate the output. Let's look at the sequence-to-sequence or encoder-decoder model. This model is based on the recurrent units like LSTM and GRU. So this RNN units, the boxes can be represented as GRU or LSTM. And this the hidden layer, these are the hidden layers. Hidden states are produced from the encoder part, either in the encoder from the previous state and the given input. You will have a previous state and the given input. And there will be weight matrices, and this will be some kind of activation function, and we'll get the new, given this, we'll have a new state. So will be encoder part. And the final state of encoding will be this part, the encoder vector. And given the encoder vector, we'll start producing the output, this part. And we'll generate based on the given hidden state, the previous state, and weight matrix. And this will be some activation function, and we'll have a next state, but also we'll create a output from the state. So this is more like a review of RNN. It's basically extension of backpropagation, and it's called backpropagation through time. And output of RNN is basically looking at the RNN again, and our output is given from the input, and then previous state will create the current hidden state. And then from the current hidden state, there's a weight matrix V, and here a weight matrix W and U and W, and we get the output from this hidden state. And one thing we notice is we'll have errors, like there'll be expected result and the real result, y hat and y, and we'll have an error. It could be cross-entropy error or some error function, and it's not just one error. We will accumulate all the errors. It's through time. So for the penalties, for particularly this one, for instance, you will get the error messages from all this, and those are backpropagated through time. About the sequence, you will use the RNN base, and these two are the basically representative papers. Elias Siskuva and Cho published these papers in 2014. And after this machine translation field, the research got changed a lot after this model got published. So one of this paper, there's the encoder part and there's decoder part. And encoder part and decoder part, they all follow the basic RNN models. And remember, this is one hot encoding of individual words, and this will be word embedding. Maybe the size of this will be 500K, and this will be 300. And this input goes into basically all these English words one at a time, and this will be this bottleneck state. And then after the state, we start producing the word in French. Right? And the size of this will be again 300 or something, and this will be again like 500K to map to the vocabulary of whole French dictionary. And training this system encoder part, like this is basically the same as this, right? So we will have the input and we'll have the output, and different languages, and training this will be using this error of all these steps, right? And not just one steps, but it will accumulate all these steps, back propagation through time, right? Remember? And those information is trained as a single system. That's important, right? End to end. So given the parallel corpus, like if you go to Canada, there are a lot of official documents. They're written in both language, like French and English. The huge corpus of huge parallel corpus of these two languages, and you can use this corpus to train this network. Just putting all this data will create this model. And one thing we just check will be the decoding. When we decoding means creating. Once this model is fully trained, we start generating words. So when we start generating, the generation actually used the input, the hidden state, but also the output of the previous state is used. So if we generate the Ju, and this will be used as an input for generating the next output, and so on. But if we have some cases, if this up is wrong, then we cannot go back. So instead of just producing one, we create the k most probable output or hypothesis, and its k is the beam size. It could be 2 or 3, but instead of just keeping one, we'll have all k most probable outputs. And it's not guaranteeing the best solution, but just close to the best solution, good solutions, and more efficient instead of keeping all possibilities, right? Okay, that's the introduction of the sequence to sequence, and this part showing what are the applications of this model. Apparently, we use this for machine translation, but it can be used for summarization. Given long text, we can create a short text, like translating long text to short text. It can be used for dialogue generation, like given the previous utterance, we can generate the next utterance. It could be used for parsing. So given text, we can create a parse structure as a sequence. It can be also used for programming language translation, right? From like Python code to Java, or from natural language to Python, and so on. And this sequence to sequence, the benefit or strength of this model is it's possible to create end-to-end. So once we define the structure and loss function, all the parameters can be learned all together. So remember the parameters in, let's see, RNN parameters, like these parameters. This U, W3, it will be trained all together. And since using this neural representation, it has just strengths of distributed representation. And the words that are similar together that mean meanings could be exploited better in this case. And also it uses context better. So by using neural machine translation, you can look at the history, meaning previous word, previous word, and so on. And you can use the context better. then the statistical techniques. It can be very, the context can be very, very long. Like ideally, theoretically, you can look at the words, 10 words before the current word, but n-grams, you can go to like bigram, trigram, 4-gram, maximum 5-gram, right? And you will have a more fluent language output than as a high quality outputs. The weaknesses include the interpretability. You don't know why the outputs are generated. It's like a black box. And unlike the old days, we cannot specify particular semantics, particular syntactic structure, or particular discourse structure, or particular anaphora, because it's all automatically generated. So we don't know where to put this. If you want to translate particular phrase to particular phrase in English to particular phrase in French, we could have used for mapping table, but since we are not using mapping table, and they are all about the weight parameters, we cannot control. There's another issue, is that, remember, there's bottleneck. So all the previous word representations map to this particular node or particular hidden state. This captures all the information about source sentence. So like if it's French is a source sentence, all the information should go in here. But if this somehow change a little bit, then the output may change a lot. That's so risky, right? And instead of keeping this as a bottleneck, is there some other way we could do this more flexible, right? Flexibly. So people look at an approach called attention mechanism. So attention provides solution to the bottleneck problem. So in the decoder side, instead of just looking the previous state or the bottleneck state, you can look at anywhere in the encoder part and focus on particular part of the source sentence. So how it does this? Now, given the current, remember this might be the bottleneck. When we start, we create this attention score across all four. There are 4 words in the input, 4 words, and we look back, not just the last state, but look back all the previous state. And how do we do that? We use this dot product. And dot product usually means similarity or kind of relevance. So we'll calculate the attention score to the current state, to the first state, and attention score to the current state and second state in the source sentence, and the third one, and the last one. And we'll have 4 different numbers. Attention score is just a real number, 4 numbers. There will be 4 numbers. And you will have a distribution of these 4 words. Now, this could be large, like 0.5. This could be 0.1, 0.1, 0.2, or something. Some distribution. And in order to make these numbers, if we have set of numbers and if we want to turn into a probability, what do we do? Yeah, we do softmax. So we make these numbers into softmax. So the bigger numbers will have a bigger, higher probability. But it will be basically normalized into the probability distribution. And we go back to the original and multiply these scores, attention distribution scores, and this will be the attention output. This will be weighted sum of encoder hidden state. And since in this case, the first one has highest attention score, this will have most information about the first state, and there will be little information about the rest state. It has high attention, the first state. And this attention output, the size of attention output will be the same as this. So if we have encoded this as 300, and this will be about 300. And we'll concatenate this 300 and this 300 together. And we'll go through some dense layer, and we'll figure out what's the output in the current state. So ill has the most relevant score. So it will be most relevant to ill, like that is he in English. And the second, when we go to the second state in the decoding, we'll also calculate the attention score. This will be some numbers, like in this case, 0.1, 0.3, 0.15, 0.7, or something. And we'll make it as a probability distribution with the softmax. And we multiply this with distribution and create an attention output. And we'll concatenate this with this and create an output. And it goes on to next and next until we hit the end of sentence. Okay, so Ilamatangte will be mapped to he hit me with a pie or something. So in summary, let's summarize all this together. We have an encoder hidden state. This n will be number of words in input. Words in input sentence. Right? So in this case will be Ilyaman Tangte. So it will be 4. N will be 4, right? In this case. And in time state, we now go to the decoder. For each decoding state, we'll get the attention score for all the individual words in the encoding. So let's say if you are in the initial state, it will be S0, and we'll have attention scores. First of all, attention scores, and then those four numbers, those real numbers, will be turned into a probability distribution. So this will be still the size of 4, but it will be summed to 1 to create a distribution. And we'll create the output encoder hidden state to get this one, right? To get this one will be weighted sum. Weighted sum. And the size of individual word will be, for instance, 500 or something. If you have a word embedding size 500. And we'll concatenate this A, this is vector 500 size, and this will be vector of 500. This and this will be concatenated. This and the current state will be concatenated 500, concatenated 500. Sorry, there's a 500, this 500, there will be 1,000. And the size will be 1,000 is still 500. And here I want to emphasize this key value, a quick key query value roles, role, right? Role. It's a role. So the decoder state plays a role of query, and the encoder individual words plays the role of key, and value will be this weighted sum. So the value will be weighted sum. The query was the current state, and the key will be individual words in the source sentence. Again, just to explain this, this will be playing the role of key. This will be playing a role of query. This once we create this weighted sum, this will be value. Okay. And when we create this, we concatenate this together and have some kind of a weight matrix. And this activation function, and create this as tilde, and this tilde will have another weight matrix, and this will be softmax distribution over this, so that we will have a size 500,000. All this different word distribution, maybe particular word like he has the highest probability, and this will be picked as the output. By having this attention, if you look at the attention, print out the attention, we can see which particular words in the source sentence most relevant. It can handle the bottleneck problem because we can use not just the last state, but also other state. And this is about the gradient disappearing. Because we can look at all the states in the source sentence. The gradient issue. If you have a multiplications, then the values may disappear if the value is less than 1. But since we're looking at, we still keep the information. That's the important part. We can look at the information, the earlier parts of the sentences, and also provide the interpretability. If you look at the attention distribution, we can see which part is important for the current state in the decoding. And alignment is automatically created. We don't have to train this. The neural network automatically generates the alignment. And this was this attention mechanism was motivation of the new architecture transformer. And this is pushing more about attention. So since still we are using RNN structure, it still have the sequential nature. Can we parallelize more? That's the question. While we are using GRU and LSTM, we have to still work on long-range dependencies. And if our sequence grows, the path length grows as well. But if your attention mechanism can access any state, maybe we can just use attention, and we don't need this sequential structure of RNN. That was the question. The guys who created the transformer architecture. So 2017, people from Google published a paper attention is all you need. And this is basically the structure. There's encoding and decoding, but it's non-recurrent encoder-decoder model. And then they demonstrate their effectiveness with the machine translation application, although they could use this for now many different application, natural language application. And this has the lot of demonstrate a lot of effectiveness in the natural language processing. This instigates a lot of evolution in language models and being able to create even large language models. If you look at the history, we have this LSTM RNN structure in late 1990s, and then there's 2017 transformers, and you may have heard the GPT series and BERT. They came out after then, and now we're in the stage of getting more and more. And this is all started from this attention mechanism in a way. So in summary of this lecture, we went over machine translation and statistical machine translation. And then we looked at the RNA-based sequence-to-sequence model. And also we looked at how attention mechanism improves the machine translation. Okay, that's all for this lecture. Thank you. Thank you for your attention.